Okay, welcome back to the class, and here we are going to look at sensing and sensors, and we do a bit of review of some of the issues in this course. The most fundamental question anybody can ask you, what is a robot? Okay, and you could have at least 2 or 3 definitions for it. Your book has also a similar definition: machines with sensing, intelligence, and mobility. That's one possibility. In order for a machine to be qualified as a robot, machine should have the following capabilities. It should be able to sense and perceive, get information about itself and its surroundings. It needs to be able to carry out different tasks. It can be reprogrammable, should be reprogrammable, meaning that for the next 3 months it could be doing something, then after that it will reprogram to do something else. Okay. That is always the case when you retool a manufacturing floor plant. Okay. And then it should also function autonomously or interact with human being as semi-autonomous situation. So why do we want to use robots? There are what this author calls it 4D environment. 1D is dangerous. There could be dirty places to work. It could be dull and tiring, and it could also be a very difficult thing to do. So if you are confronting any of these, robot is the one which is actually going to be able to help you. The most important one is the dangerous one, where human life should not be jeopardized. That's why you have robots in what we call master-slave mode, where a master robot is far away from the danger zone, and through cameras and vision you can see what's going on inside that dangerous area, and the master robot will do tasks where the slave robot inside that danger zone will follow. Okay? When the nuclear bomb was created in the late 40s and early 50s, many laboratories, including our own Oak Ridge National Lab here in this country, were using that technology, master-slave robotics. Okay. And, or if you put robots thousands of meters under the water, where human cannot survive. Okay. And for a tasks, you can use them for automating, use it for automation, augmentation. If you have something which is working but not perfectly working, so you could augment a robotic task to one part of this to make it into a more efficient situation. And it can be used for assistance, like assistive robotics for elderly and people with disability and so forth. And it can be used for autonomous applications. A good example of that is Mars rovers that NASA has sent to Mars. Okay. So these are types of robots. You have manipulated robot on the left. You have wheel robot. You have legged robot, or locomotion type of underwater robots, aerial robots like quadcopters and helicopters and so forth, or you could have humanoid robot. Okay. In this course, we have given you some exposure to this and some to this, and for some of you here and some here and some here. Okay, we've covered quite a few of these kind of robots. This locomotion is much more expensive to build and to do, and some of the full body locomotions are possible, but it's very, very expensive. So locomotion are, as you saw in discussion in, I believe, chapter 4, you had a bicycle command in the toolbox. You have a differential drive robot. The two velocities of the two wheels or rear wheels are the control variables. And then you would like to look at three variables: X and Y coordinate of the center of the robot, center of gravity, or similar to here. You have an idle wheel here and two controlled wheels here. And then the direction, the orientation of the robot moving in addition to X and Y coordinate. You could have a special wheel, that the Swedish wheel, which we have it on our 3D printed robot in the ACE Lab number 2, that you have seen it, which can move in XY location and it could go side like that. Or you could have synchronous drive. You could have 3 robots working together, like the one that the students are doing in ACE Lab, ACE Field Lab. So locomotion is the process of causing a robot to move. Okay. So this is the dynamic model of the typical wheeled robot, right here. The V and omega are the left, related to the left and right velocity, and theta is the orientation of the angle of here, this angle, right here. And we have non-holonomic constraint, which means system whose state depends on the path taken in order to achieve it. So here is the angle theta, and the non-holonomic constraint, meaning x dot sine of theta minus y dot cosine theta is always 0. That is a specific distinguisher this robot from other type of robots. Most robots are non-holonomic. So x and y coordinate and theta are the variables here. These are your state variables. This is your nonlinear dynamic model. Okay. And basic motion control, again, you have a straight motion where you have these two velocities are equal. If they are different, then you basically are moving to the left or to the right, and so forth. If you are rotating around, one is negative of the other, and the robot is just moving around. Okay. So these are some references for sensing and sensors. Sensor for mobile robots. You can see there's a whole book dedicated to that, and another book dedicated to it like this. And these are some references for you. So, again, we are going through a whole bunch of different sensors that you saw some of them in the orientation lecture. This is getting much more elaborate and a bit more details. So again, collect information about the world. That's sensing. Sensor is electromechanical device, which mechanical or chemical device which maps environmental attribute quantity measurement, and each sensor is based on transduction principle. Again, conversion of energy from one form to another. Thermostat, temperature, electrochemical chemistry to voltage, photocurrent, light intensity to current, pyroelectric, thermal radiation to voltage, humidity is humidity to capacitance, length linear variable differential like transformers or position to inductance. And microphone, sound, pressure to anything, anything you like. Human sensing and organs. Vision corresponds to eyes. Hearing, ears, acoustic and sound. Touch is a skin or tactile sensing, a skin type. Because when the manipulators were first invented in 1950s, if they were not able to invent tactile sensing, there was no use for the robot to be able to work in the environment, to be able to pick things up. So if the robot needs to feel an object before it tries to lift it, okay? So tactile sensing and a skin type of mechanism that we take it for granted in our human behavior is very important. Odor, noise, wafer phase chemistry is another one which is important. And then taste, you could have your tongue, liquid phase chemistry, okay? Now, looking at ranges and modalities. Vision outside of the RGB spectrum, for example, infrared camera, seeing at night, okay, which is very difficult for bare human eyes. Active vision, radar and optical or laser range measurement. Hearing outside of the 20 hertz to 20 kilohertz range. This is the range of the human being, right here. Ultrasound is beyond that range, outside of that range, which only bats and dolphins can do in terms of species. Very few can do it, okay? And therefore you need to build the sensor for that. Chemical analysis beyond taste and smell. Radiation of various different rays, alpha, beta, gamma, neutrons, and so forth. In electromagnetic spectrum, you can see here a large spectrum of different frequencies and wavelengths and the amount of energy in terms of photon or electrovolts. So I let you review and look at it later. Classification of sensors. Like before, some are external, some are internal. Okay. If you have, for example, feedback of a robot internal parameters like battery level, wheel position, joint angle, those are internal ones. Observation of the environment objects using external camera is external sensors, which you gather information about it. Okay. Active versus non-active sensors. Emitting energy into environment like radar or sonar, or passively receive energy to make observation like camera. You need to see whether the robot has to contact or non-contact missions or capability. Can it have visual or non-visual? Vision-based sensing, image processing, video camera. Many applications are, as I said, for example, for that particular project of Nico's group are using vision feedback to control 3 ground vehicles. Okay. So these are sensors in a nutshell of being used on various different robots. You can see gyros, gas sensors, flexible or bend sensors. You could have touch sensors, and you have ultrasound transducers, compasses, different kinds of solar cells, IR modular, IR amplifier sensors, and so forth and so on. And many, many different potentials. So, what sensors are being used in robot navigation? Resistive sensors, bend sensors, potentiometers, resistive photocells, even encoders. Tactile sensors using contact switches or bumpers. Okay. Infrared sensors. This is beyond the human's capabilities. Reflective or proximity or distance sensor. Ultrasonic distance sensor, inertia sensor measures the second derivatives of the position, accelerometer. Okay. And gyroscopes are also used for balancing the robots or vehicles. Orientation sensors, compass is one of those. So which direction are you heading? Inclinometer, for example. Laser range sensors, vision and GPS sensors. One of the things that I would have, if I had thought about it, I would have looked in preparing for this lecture. I would have tried to find out, if possible, what are the sensors on a driverless car? What are the group of sensors on those cars? Okay? I would imagine it's beyond what I'm giving you this lecture. I imagine it could be propriety of manufacturers. But nowadays there are at least 6 or 7 companies around the world who are actually building and commercializing driverless cars. Okay. I recently saw an elderly lady behind one of those driverless cars, a video, and she was really very tense and didn't know when it's going to have the crash, when it's going to stop, what happens to me. You know, she was screaming and so forth. And you know, the car was okay. Okay. And now the lawyers are trying to figure out what happens, how to sue somebody if a driverless car hits you. Okay, the manufacturer of the sensor or the company who sold it to you or what? Resistive sensor. You saw that before. You know, we have a bend sensor. You know, you have a variety of range of resistance, and depending on what location that, let's say, if this is attached to a flexible robot, for example, you know, this is the kind of robot that you could also use it for a snake robot. The one, not exactly the way that we built it, but some other ones are looking at that. And high dimensional degree of freedom for those kind of robots. Potentiometers and can be used as a position sensor for sliding mechanism or rotating shafts, easy to find, easy to mount. Light sensors are photocells, okay, like these. Basically, you shine on it and it gives you a measurement of the voltage proportional to the intensity of the light. And they have a nonlinear resistance in it and slow responses. So, sensor needs to know what is the joint, what's this angle, how far do I bend? Or wall following. Here is a whisker. These are like whisker robot, whisker sensor. The whisker stands beyond the body of the robot, hits the wall and knows where it is. Okay? Just like this diagram shows. Or you could have a weight sensor. You're lifting something and this will push on this spring and then the sensor picks it up right here. Proportional to the. Of course, you have to, time to time, you need to calibrate your sensing mechanism. You could have inputs for resistive sensors. You could have a constant voltage, and then you could divide it. And then that is how you divide the voltage here. Okay. Or you could have a binary threshold, a plus or minus here. if voltage is at plus is greater than at minus digital high. Infrared sensors. Intensity-based infrared reflection sensor, which sends a signal like a laser beam to an object and waits for it to bounce back and receives it, and then a process which I'll explain now or next lecture. Through triangulation, you would know what it is. Triangulation is you measure the speed of your light, you know the time it travels, then you know that distance. And then you do the same thing on the coming back, then you know where you are. GPS is using triangulation continuously as you are using it, while you are driving or you are walking and so forth. Modulated infrared proximity sensor, which doesn't need to be too accurate, but you just need to know I'm going this way, what is around me, so you are aware. Requires modulated IR signal, infrared signals, insensitive to ambient light, which is good. Infrared ranging, distance sensors, short range distance sensors, and so forth. So, intensity-based infrared, basically, as we said, you transmit a signal, okay, like a light signal, and hits the another one. You could basically measure the distance between these two sensors, or you could have an emitter hits an object in the environment and wait for it to bounce and you measure it. Okay. Then this process is called reflective sensor. Okay. That one is called break beam sensor. Looks like this. Okay. So very often it's relatively easy to use, and again, but it is sensitive to ambient light, which is not good. Same thing here. Now, modulated infrared, modulation and demodulation. Flashing a light source at a particular frequency. That's first step. The modulator is tuned to the specific frequency of light flashes between this range. Flashes of light can be detected even if they are very weak. They are less susceptible to ambient lighting and reflectivity of objects, and they can be used in most infrared remote control units, proximity sensors, and so forth. And this is how the anatomy of a proximity sensor looks like. You have a ground here, you have a voltage coming out, you have the light emitted on it, you have amplifier, limiter, band pass filter, and so forth and so on. IR distance sensors. Basic principle is you have IR emitters, like for example this emitter, focusing lens, which is with your focusing lens, position sensitive detector, here, a detector here, or a position on the place you want, and then you detect it here, and then this triangulation right here allows you to know where that thing is, where this is, okay. You also could have modulated IR light, which is modulates here. This is some commercial GP2 D02 IR Ranger put out by a company called Sharp, the Japanese company, and it looks like this. You have here, I think, looks like a 25 cents coin. Distance ranger is about 10 centimeter or 4 inch approximately, up to 80 centimeters. Moderately reliable for distance measurement. It's immune to ambient light. It's impervious to color and reflectivity of object. Applications are distance measurement, wall following, and so forth. So this is how the encoder works. There are two kinds, incremental encoder. What you have here is the motor. You have a shaft. Encoder is mounted on the shaft. The light source sends the light through, and then it's being detected here. And light goes through these holes. It doesn't go next. It goes through that and so forth. As this rotates, you have a pulse, sequence of pulses coming out. Through those pulses, they detect the velocity of the shaft. It generates pulses proportional to the rotational speed of the shaft. Direction can also be indicated with two-phase encoders. So you have two-phase encoder A and B. You can go this way or that way, clockwise or counterclockwise. That's the incremental one. Absolute optical encoder actually manufactured with a whole bunch of holes on it in a very organized fashion. You have a light source, a beam expander, you have collimating lens, putting all the 10 together, send them into a cylindrical lens, and then runs through the encoder and detect here. And then you code the binary and the gray code bits to be able to estimate the velocity of the shaft. Odometry sensors, resolvers. What are resolvers? Resolvers are devices which have two stator windings, position at 90 degrees. Here is one stator, this is shown here. This is another stator. They are at 90 degrees from each other. The output voltage is proportional to the sine or cosine function of the rotor's angle. Okay, the rotor is in the center here. And as you know, the rotor is rotating through this magnetic field, which is created by these stators. And then that's how you generate mechanical energy, rotational energy, based on the conversion of electric energy coming from the voltage sources, VT here, and VY, and V, and they look like this signal. Okay. The rotor is made up of a third winding C, which is this one. Potentiometer, you already seen it many times. Okay. Range finders, ultrasonic and laser. You time the time of the flight of the light going to hitting the detector and coming back. The measured pulses typically come from ultrasonic, radio frequency, and optical energy sources. So you multiply the velocity by time, you get the distance. This distance is the round trip distance, going here and coming back, or going here and coming back. And T is the elapsed time, V is the velocity of the wave propagation. For sound, it is 0.3 meters per millisecond. For RF or light, it is 0.3 meters per nanosecond. Very difficult to measure short distances between 1 to 100 meters. So ultrasonic, again, above human ear sensors. Those are sensors which, again, emit a quick burst of ultrasonic, 50 kilohertz, to the here, hits the environment, hits the object, and the wave is going to be bounced. It used to come this way, now it's going that way. And then it's detected by this receiver. Okay? And as we said before, no moving species except bat and dolphin can do that. And maybe a few more that I don't know, and the otter they know. Okay? So, again, more of ultra sensors. In the older days, Polaroid needed to have an ultrasonic ranging system for the autofocus of their camera. You know, Polaroid is a a pioneer company in this country for ready-to-use pictures. You basically take a picture with it, it's about this size, like this, and you take a picture after, and there is a chemical built in the film itself, and you pull it out of the camera, and you wait for maybe 2 minutes, and you see the picture. Okay. So they needed to put an ultrasonic transducer on their camera to be able to provide autofocus for that camera. In the 90s, we had a Grant with Polaroid in my previous job, and they actually had a Polaroid camera attached to a CCD camera with a long tunnel, and they were taking picture of, let's say, monitor of your computer with some pictures or some what have you. And then when they were printing it on the Polaroid camera, it didn't come out too clear, too very good. And I was teaching a course at MIT Lincoln Lab at that time on fuzzy logic. Okay, and the company thought fuzzy logic can be used in it, and they were right, because their experts, their operators would have to play with adjusting many things of the camera before they take the picture, and then even that, the quality was sometimes not as good as they had hoped. So what we did, we got a contract with them, and we put fuzzy logic in place of that expert. We put fuzzy if-then rules, expert rules, and were able to adjust 5 attributes for every pixel of the image: color, contrast, tint, 5 different attributes. And we actually got the US patent on it. Okay? And we're able to, and then my university sold it to a company in Washington. Okay? And so the autofocus, it could have been done alternatively rather than using something like this. And this is how it works. Now, suppose you have also distance measurement. You have a robot here in an enclosed environment. You have a door open, and you are using proximity sensors. You scan the entire room, and you hit the chair, and you get it bounced. You say, something is in the room. And then the lighting of length of the echo versus a scan moving from left to right. When it reaches the chair, it's somewhat here, and then it goes to the doorway, goes way out, and you can't even, the largest amount you can have. So you can scan it at an angle of 15 degrees apart, and that can achieve the best part. You see 15 degrees here, 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 15 degrees around. Okay. So noise issues, again, noise issues is also another potential issue, especially when you are working at night and everything is so quiet, and you can measure the slightest amount of noise and use that. The SICK laser rangefinder you saw before, it's again sends the laser signal and gets it bounced and measures all the distances and so forth. Inertial sensor, gyroscope, which measures the rate of change of rotation independent of the coordinate frame. Common application, heading sensor, full inertial navigation system, of course on many different vehicles. Accelerometer, which we also have it on our robots in ACE Lab, measures accelerations with respect to an inertial frame, common application, thin sensor in a static application, vibration analysis, food inertial systems. More on accelerometer, they measure the inertial force generated when a mass is affected by change in velocity. And this is what force can do for you. And this is how an accelerometer works. You have a sensor which consists of a mass spring dashpot combination, shows here in a Newton's equation. High quality accelerometer includes a servo loop to improve the linearity of the sensor. So you have a mass, you have a suspension mechanism, number two, and a sensing element. Okay, that's the sensing axis. So if it moves in and out, you can measure the acceleration that way. Okay. In other words, acceleration is right here. It's going to be F minus this divided by m. That's how you measure it. Gyroscopes, these devices return a signal proportional to rotational velocity. There is a range, large variety of gyroscopes that are based on different principles. So GPS. In GPS you have 24 satellites and some spare ones which are rotating around planet Earth. And they broadcast time, identity, orbital parameters, latitude, longitude, altitude to the Earth. Okay? And they run in real time. And you can actually even go to a website and watch it change. So you have a ground antenna, you have a master control station, you have monitoring station, and how does it work? In a minute I'll tell you through triangulation. And we use it in GPS, triangulation. Idea behind GPS is to use satellite in space as a reference point for locations here on Earth. Very, very accurately measuring our distance from 3 satellites, we can triangulate our position anywhere on Earth. So, I will give you in a few minutes, or maybe next lecture, we will have that.
Last slide, Professor.
We have real sensors are noisy, origins are natural phenomena, less than ideal in engineering. Consequences, you have limited accuracy and precision of measurement. You have filtering, software, averaging signals, and algorithm and hardware is somewhat tricky, like capacitor. So I'll stop here and we will continue next hour.